So in the last video we talked about matrices, what they are, why they're important to us. We also talked about matrix multiplication. But bringing up matrix multiplication brings up another question of what is the inverse of matrix multiplication? So first of all, I want to just briefly go over what is an inverse. So inverses are actually something that whether you know it or not, you're probably pretty familiar with. So let's say, let's go over an example of an inverse that you most certainly know. So let's say you have some integer, I don't know, 5, and you want to say what's the inverse of 5 in respect to multiplication. So what is a number b such that 5 times b is equal to 1? And you might be saying that seems kind of arbitrary. Why we're bringing 1 in here? That's because 1 is what we call the identity. This is the identity element for multiplication. So to put in some fancy math, actually, no, I'm not going to draw the math symbols as much as I really want to, but essentially 1 times x equals x for all x in the set of reals. So this is so 1 times x is equal to x for every real number, even for every complex number too. But this is essentially the definition of an identity element. So an element such that that element, when you do an operation between that and another element, you get the x back. So in this case, you should all probably know that b is equal to 1 over 5. So let's just do another one real quick. So let's say you have 10 plus x equals 0. So this is another case where the identity element is 0 because x plus 0 equals x for all x in the set of reals. So this is just fancy math notation that you'll learn in 2500. It essentially just means for every x that is a real number. So 1 plus 0, or x plus 0 is x for all x's that are real numbers. That's all. This is just a condensed way to write that out instead of writing this out all in words. So then you might be asking yourself, how do we find the inverse for matrix multiplication? Does there exist an inverse in matrix multiplication? So first of all, to find how to get an inverse, we first need to identify the identity element. So the identity element for a matrix is, so A, B equals A for all, for all A's in the set of Rn. So this Rn notation here just denotes, so real matrix. That's what this Rn thing denotes. Actually, that's not perfectly true, but just know that A is a matrix, and you want to find a B so that A times B is equal to A. So again, just to kind of give you the answer instead of deriving the answer, so B is going to be equal to just 1s going down the diagonals, and otherwise they're all 0s. So it'll just be 1, that's not a good one, 1, 0, 0, 1. So the rest of these are going to be 0s. The rest of these are going to be 0s. These are going to be 0s. And this next diagonal is going to be a 1. And you see this 1 goes down the diagonal for as many elements as you need. So this is what's called a square matrix, meaning that, also we call this I. So that's important. I, just for identity, just keeps it simple. So this is the notation for anytime you want to talk about the identity matrix. It looks like this. And this identity matrix is actually special not just because it's an identity matrix, but also because it's something called a square matrix, meaning I of n is n by n. So it has n columns and n rows. So let me think. I think I'm not going to necessarily justify why this is the identity, just for the sake of time, but if anyone wants me to do a quick video justifying why this is the identity, essentially just proving that AB is going to be A for any matrix, I can do that, but otherwise I'll just skip that detail for now. The important thing to remember from the last video though is that, so if A is n by n, this implies that I is n by n, and this is because of that matrix multiplication rule we talked about before, where these two dimensions need to match, or these two rows and column element amounts need to match. So yeah, there's that. So then the question becomes, how can we find the inverse of A? I'm not necessarily going to go over how to find the inverse, just because that's a pretty complicated process that you're going to learn in matrix algebra. It's not necessarily important to know how you get the inverse right now. It's just important to know what the inverse is. So when we write the inverse of A, so we have A and the inverse of A. So the inverse of A is just equal to, we denote it like this, or A minus 1. Similarly to how for multiplication we had B is equal to 1 over 5, there's literally just 5 minus 1 to the power of minus 1. So yeah, but it's not as simple as just flipping all the values, like taking the reciprocal of all the values in A to get the inverse. It's not as simple as that, because if you remember, the matrix multiplication process is fairly complex, and it's actually true that not all matrices have an inverse. Anyway, another thing that's true is that, so A inverse is equal to A inverse A is equal to 1, or I. So you might be saying, like, why are you putting this down? Why is that important? Shouldn't these two things be equivalent, like, no matter what? And that's actually not true. So when you have some matrix multiplication operations, you have A, B, that is not necessarily equal to B, A. And I can prove that really quickly. So if A is P times N, B is N by M, then you can do A, B, because the N's match up. So you end up getting P times N, N times N. And you see these two N's match. But then if I do B, A, I'm going to get N times M, and then P times N. And this does not exist. So that's just a quick proof just showing that AB is not necessarily equal to BA. So I think that should wrap it up, except for one more property I just want to talk about. For all matrices that have an inverse are going to be square matrices. So if you have some matrix A and A inverse exists, then A is N by N, which is square. And then square should be pretty intuitive in that, like, if you have as many rows as columns, it's going to look like a square. So 1, 2, 3, 4. That looks like a square. So that's the quick overview of the inverse. Next video, I'm going to go into the transpose So the inverse, we won't use too much in application, but we might use it in some derivations. There's actually one equation that we're going to use it in our first model, which is why I'm going over that. Well, I'm going over this now, and also because I wanted to write some math notation, because I'm also a math major. So yeah, thanks for watching.